Okay, right. So I'll start off kind of back to the basics that we've seen a few times throughout the workshop. We're going to assume that our LIGO data, here denoted to be in the frequency domain with the tilde to denote the Fourier transform. So our data is the sum of a noise component and an astrophysical contribution that depends on some astrophysical parameters that we're interested in measuring. Usually, throughout most of this talk, these will be the 15 parameters describing a quasi-circular compact binary merger. So we've heard this before, but we typically assume that the noise is both stationary and Gaussian. And so in this case, the noise covariance matrix can be characterized by the power spectral density. So if you take the Fourier transform of your noise and multiply it by its complex conjugate, and then take the expectation value of this quantity, you will get a hopefully diagonal covariance matrix that is proportional to the PSD multiplied by the duration of the segment that you're taking the Fourier transform of divided by 4. And so for most of this talk, we're going to assume that this assumption of diagonality is true, but then I might highlight a few situations where this is actually not a good enough assumption. Okay, so for well-behaved noise in the absence of a signal, the real and imaginary parts of the strain will each separately follow a zero mean Gaussian distribution that has a variance given by, again, this noise covariance matrix. So this variance will come up a few times. And we can see an example here of some noisy LIGO data that has been colored by this power spectral density. Basically, if we take the data and divide it by the square root of this variance, and then in each frequency bin, we can take a histogram and basically just take those whitened frequency components. You can compare it to a unit normal, and you can see that in this assumption, the noise follows this unit Gaussian distribution. So once we introduce a signal, we have to shift from working directly in the noise to working with the residual. So the residual is just the data with the astrophysical contribution subtracted. So once you add in the signal, it's now the real and imaginary parts of the residual that should be Gaussian distributed. So here we can see something akin to the likelihood function that we've seen a few times, where it's Gaussian in this residual, but for each of the real and imaginary parts separately. And in this case, this sigma here is the same as before. So again, the variance is just the duration times the PSD divided by 4, but the total likelihood is the product of the real and imaginary components. So it's not the total likelihood that is Gaussian, it is the individual likelihoods that are being producted here. And this is something that I want to stress because it's often kind of swept under the rug in the literature, and we say the likelihood is Gaussian, but it's actually not a Gaussian. It is this quantity called the Whittle likelihood, and you can see it written out in full here. So there's actually no square root out front in the normalization factor because you've taken your two real and imaginary individual Gaussians and multiplied them together. And then the term in the exponential is unchanged. So this is frequency dependent for a single frequency. And then when you want to look at data across the full range of frequencies, you just multiply your likelihoods for each of your individual frequencies together. So far, we've assumed that this quantity S sub n of f is known. However, in general, we can only get an estimate of this true PSD. In no case will we ever be able to precisely determine the exact power spectral density that characterizes LIGO noise. So there are typically two methods that we use to calculate this PSD. The first is called the Offsource Method, also called the Periodogram Method or Welch's Method. And how this works generally is you take a long stretch of data that is either before or after, but always excluding the segment of data that you want to analyze. And this is why it's called off-source. And the reason we do this is because we know that there's a signal or something of interest that is non-Gaussian and non-stationary in the particular segment that we're trying to analyze. So if you include that segment in the estimate of the noise, you'll get a biased answer. So we take our long stretch of data and we split it into individual short segments, and we calculate this quantity called the periodogram for each segment after we've windowed the data. So first we split it up into short time segments, window each of those segments, and then take the Fourier transform and the absolute value squared of that Fourier transform. And so the reason that we need to window the data is because LIGO data are actually not periodic on the interval of time that you're using to divide here. And so the window basically imposes periodic boundary conditions at the edges of the segments, and it suppresses spectral leakage in the resultant PSD. And then once we have this periodogram for each of our small segments, we take an average of it, so either the median or the mean, and I'll talk about both of those methods in a bit. And here you can just see an example of a PSD that's been calculated for some simulated LIGO data. In blue, you can see the PSD calculated from a 64-second segment, and in orange, the PSD for a 512-second segment. So unsurprisingly, there's less of this fuzziness for the PSD that was calculated with the longer stretch of data, just because you're averaging over more points in your periodogram to get the resultant PSD. Okay, so there are two corrections that need to be applied when you use this off-source method. The first is a window factor. So when you window your data, here you can see an example of two different types of windows that are commonly used in gravitational-wave data analysis. You're actually removing power from the data by making it go to 0 at the edges. And so you need to correct for this loss of power by multiplying by this known window factor correction. So it's just this the square of the value of the window at each of the time segments, summed and then divided by the number of time segments. So this window factor needs to be applied generically every time you've windowed data. So we'll actually always have to window the data, even with the other on-source method that I'll talk about. So it needs to be applied there as well. And it's another thing that's often swept under the rug. The other thing is the median correction. So typically, in gravitational wave data analysis, we say we're going to use the median instead of the mean in the Welch's method because we know that our data actually aren't Gaussian and stationary, so the median will be more robust to outliers. However, the median is a biased estimator of the expectation value, and so we need to correct by this known correction. And here, this is assuming that you're averaging over an odd number of segments. So you're pretty much just including this correction over the number of segments that you're averaging. Okay, so that's how we calculate our point estimate for the PSD, but this method has some inherent uncertainty in it. And what we want to do is just derive that uncertainty. So we can define, for convenience, a normalized periodogram for a single segment that I'll call Q sub L. So this is just our periodogram and then divided by the variance that we saw before. And if we were to dissect this Q, it is the quadrature sum of two independent standard normal random variables. So it's the sum of the imaginary part of the data squared that's been normalized and the real part of the data squared that's also been normalized. And it turns out that the probability distribution of the quadrature sum of two standard normal random variables is the chi-squared distribution with 2 degrees of freedom. So because we know how the real and imaginary parts of the data are distributed, we also know the probability distribution of this normalized periodogram. And now we can just use this distribution that's known to calculate the probability distribution of the true PSD given the PSD that we have estimated. Okay, so to start off, we'll just make the simple assumption that we're going to use the periodogram of a single segment as our estimator of our PSD. And in this case, our estimated PSD, which we'll call S hat, is just QL multiplied by the true PSD. And we can define a new quantity, some global Q, which in this case allows us to go from the probability of QL that we already know to the probability of the true PSD. You just apply this factor of the Jacobian here, and we know that the probability of Q given our estimated PSD is just this chi-squared distribution with 2 degrees of freedom. Okay, so that's what this looks like for a single segment. We can now extend this to look at the mean of a bunch of segments. Okay, so in this case, our estimator of our PSD, S hat, is defined in this way. So it's this sum of the periodograms from individual segments. You have to multiply by your 4 on T, and then you just take the average. So this quantity here, the sum of QL, is also chi-squared distributed, this time with 2 times the number of segments, degrees of freedom, because for each segment you have 2 independent standard normal random variables that you are summing, and then you're summing over them for each of the n segments. And so again, we can just do a change of variable and end up with our final probability distribution for the true PSD, given the estimated PSD as the mean of a bunch of different periodograms, and it looks like this. So here's your chi-squared distribution with 2 n degrees of freedom. Okay, how about for the median? We've said that we prefer this method for gravitational wave data analysis because it's more stable to outliers. So here we're defining our estimated PSD as our true PSD divided by this median correction times the median of the individual periodograms in each segment. So again, this is a median that's being taken frequency bin by frequency bin. And if we are working with an odd number of segments, then we can use order statistics to obtain this pi of Q distribution because we know in this case that we'll have half of the segments being less than the median that we've estimated and half being more. So I won't go through the gory details of the median order statistic derivation, but keep in mind that this is how we obtain it. Okay, so that was for the offsource method. We showed how to calculate it and the various statistical uncertainties associated with it. We can now switch to talking about the onsource method, and Tyson Littenberg gave a nice introduction to this in his talk on Monday. But basically, in this case, you try to infer the PSD using only data from the segment that you are analyzing. This is why it's called onsource. And so the PSD is modeled as the sum of a broadband spline with narrowband Lorentzians to fit the spectral lines. So you can see an example PSD here. And this is implemented in the baseline algorithm. And so what you do is you actually perform Bayesian inference to infer the parameters of the spline and Lorentzians that best characterize the noise in the segment. And the advantage here is that it requires significantly less data. So if you're analyzing a 4-second segment, you're only requiring the 4 seconds of data in that segment to be stationary and Gaussian, as opposed to on the offsource method, you're averaging over many 4-second segments. And so the required stretch of data that needs to be Gaussian and stationary is much longer. And so it's more likely that your short segment will actually follow those statistical assumptions. Okay, so what is the associated uncertainty with this measurement? So for each of the posterior samples that we get on the spline and Lorentzian parameters, we can construct a posterior on the PSD. And you can see an example here of this PSD posterior distribution for GW 15, 10, 12, which was one of the weak signals detected in LIGO's first observing run. This is for the Hanford detector. So in blue, you can see some of the individual PSD posteriors, and in black is the median. And there is some variation, at least for this event. You can see here at around 80 hertz, some of the posteriors pick up this extra bump, and there's also some strange behavior happening at low frequencies. But typically what is done is we just ignore this uncertainty and take the median PSD posterior. But in reality, the true PSD is equally likely to correspond to any of the curves in the PSD posterior here.
What do you mean by median when you're in a high-dimensional space like that?
Yeah, so basically you plot all your PSD posteriors, and then in each frequency band, you take the median value of the resultant curves. Okay, there is an alternative parametrization that was also explored in the literature that's kind of a hybrid approach between the two. And so you still have to estimate your PSD using the Offsource method, but in this case, you add some scale parameters to the Offsource PSD estimation, and the values of the scaled parameters are inferred simultaneously with your astrophysical parameters. So in this case, our known PSD becomes some estimated Offsource PSD multiplied by these scale parameters. And in the implementation in these papers by Tyson and John Veach, they had 8 bins, each corresponding to one of these scale parameters. And so they were log normally distributed, meaning that each covered a different number of frequencies. And they assume the prior on this scale parameter is a normal distribution with mean 1 and variance 1 divided by the number of frequency bins covered by that scale parameter. And so this reduces to the off-sourch uncertainty in the limit that there is 1 scale parameter per bin and that this Gaussian prior is replaced with a chi-square distribution. So this is kind of a flexible approach that lies in between the two. Okay, so now we've understood how to calculate the PSD and quantify the uncertainty on that measurement. How do we actually marginalize over that uncertainty when we're doing inference? So we can just treat it as any other parameter and integrate it out. So here we have our likelihood. This is our Whittle likelihood that we saw a few slides ago, multiplied by the probability distribution of the true PSD given our estimated PSD. Or in the case of the hybrid approach, this would be your priors on those scale parameters. And then you just integrate this true PSD out. And so in general, your likelihood always depends on the estimate of the PSD that you're using. It's just usually suppressed because we normally take the estimate to be the true value. So this works well for the off-source method. Alternatively, if you already have a PSD posterior, so maybe you've run the onsource method separately as a first step, then you can do a similar marginalization directly over the posterior instead of in the likelihood. So we can write our joint posterior on the binary parameters theta and the true PSD as the product of the posterior on the binary parameters depending on that true PSD and the posterior on the PSD. Okay, so what actually happens when you do that marginalization? For the off-source mean method, what you end up with when you analytically marginalize the Whittle likelihood over that prior is what's called a student Rayleigh distribution. So this was first derived in the context of gravitational-wave astronomy and some papers by Christian Rover. And this is just a student T distribution with 2 times the number of segments, degrees of freedom. So this is basically like a Gaussian, but with heavier tails. And so it allows for you to have outliers in the noise compared to a regular Gaussian. And this is the functional form. It looks somewhat akin to a Gaussian, but the exponential is gone, and you've introduced this factor of n, which is the number of segments here. Okay, so if instead you use a median average, then you can do the same thing. Again, you remember that your uncertainty is given by this median order statistic, and this was derived in a paper by Colin and Eric Thrane last year. And this is the resultant distribution. So this is pretty unwieldy compared to the Whittle likelihood that we saw at the beginning. And in practice, this is numerically unstable. So how this is implemented is you construct an interpolant over the integrand, and then you can evaluate that quickly at runtime. Okay, and for the onsource method, we can use our favorite hammer that we heard about earlier in the workshop, which is just perform a Monte Carlo integral over the individual posteriors for the PSD that we already have. So we can take our integral and just write it as a sum. And in this case here, these posteriors are on the binary parameters given a particular choice of the PSD from the posterior that you already have. And so in this case, the PSD marginalized posterior on these binary parameters is the combination of an equal number of posterior samples obtained using each posterior PSD. So in practice, this means getting hundreds of posteriors on the binary parameters, one set corresponding to each posterior PSD.
Can I ask a quick question on
that?
So I missed the first talk where this was done, but like the fact, I mean, it's on source, so if there is a signal there, then it's going to influence things. And I would guess that the probability of SN given data would also have like a theta in there.
Yes. So how this works in practice is when you estimate the PSD with the Onsource method, you also simultaneously fit the signal. But in most cases, I'll show a recent paper by Katerina that shows how to do this kind of all in one. In most cases, the signal is fit just with sine Gaussian wavelets. And so basically you assume that the signal is coherent in both detectors, whereas any sort of glitch or other non-Gaussianity is incoherent. And so you're actually, in the process of estimating the PSD, you'll also get posteriors on any sort of coherent signal and incoherent non-Gaussianity. So this is not biased by the presence of the signal in that segment. Yeah, so this is already marginalized. Like this posterior is already marginalized over the posteriors that you get on all those other sine Gaussian wavelet parameters. Okay, so some caveats. All the approaches to marginalization that I've presented so far still assume that the data used to calculate the PSD are Gaussian and stationary, and we know that's not always true. So for the analytic off-source marginalization, again, it requires a longer stretch of data to calculate the PSD estimator. And because of the analytic nature, it's not easily extendable to incorporate off-diagonal elements of that frequency domain covariance matrix, which is actually necessary in some of the situations that I'll show at the end. And if, for example, you wanted to look for a stochastic background, then you assume that there's some correlated cross power between the two detectors, and so your likelihood can't just be the product of the likelihoods in the individual detectors. You need to include these off-diagonal cross-power terms, and so this method does not generalize to that sort of cross-power likelihood. The numerical on-source marginalization is amenable to these sorts of modifications, but it requires you to obtain posterior samples on the binary parameters independently for hundreds of PSDs. And in the current implementation in Bayes-Wave, you can't get out evidence for the PSD marginalized hypothesis. So pros and cons for both approaches. Okay, so just as a brief digression before I show some results on this, in practice, this PSD marginalization is computationally expensive in some cases, and so it's implemented using the technique of likelihood reweighting, also called importance sampling. And it was introduced in the context of Gravitational-Wave astronomy in a paper by Ethan Payne and others. So basically, the idea is that you construct some weights, which are the ratio of your target likelihood with some hypothesis H1, which is usually more complete or more computationally expensive compared to your proposal hypothesis H0. And so you can basically start off by just analyzing the data under your simpler proposal hypothesis and then reweight it into your more complete target hypothesis. And this allows you to get evidences and posteriors. And if you're interested in more details on this, you can see a nice poster outside by Basil. And so you might be thinking, this requires the target and proposal likelihoods to have support in the same parts of the parameter space. I'm not sure I really trust this method. So for the applications that I'll talk about at the end, this was the method that was used in almost all situations. And the efficiency of this method was greater than 95%. So for the situations where this is actually important, at least for the off-source marginalization, this is good enough. And it could also be used in the on-source marginalization. So maybe in that case, your proposal hypothesis would be just analyzing the data with the median PSD. and then your target likelihoods would be changing the PSD in each case. We haven't tested that out to see what the efficiency is like for that sort of situation, but it might be a way to reduce that computational cost in the future. Okay, so now we can look at some posteriors and base factors that we obtain including this PSD marginalization. So these results are from the same paper by Coleman and Eric Thrain. And here you can see the posteriors on the chirp mass, right ascension, signal-to-noise ratio, and declination for the same event GW15, 10, 12 from the first observing run. And the different colors correspond to either different averaging methods used to calculate the PSD or including or not including that analytic marginalization. And so the bigger difference is actually between the mean and median PSD calculations rather than including or not including the marginalization. And this is somewhat expected because you're just changing the PSD more drastically in that case. Looking at these posteriors, though, you might be thinking, oh, there's basically no difference. I would tend to agree with you. But where the big effect is in the base factors. So here, this is the natural log base factor comparing the marginalized versus unmarginalized hypotheses. And you can see that for both the mean and the median, there's a statistically significant preference for the marginalized hypothesis. So including that uncertainty in the PSD gives you a better description of the noise in the detector. So this variation in the base factors will be important later. Okay, we can also look at how this works for the hybrid approach. So here in this paper by Tyson, they actually perform parameter estimation on the same compact binary signal, but they use 300 different PSDs that were calculated using different segments of time in initial LIGO data. So this is a simulated signal that's been added to real initial LIGO data. And here they're showing the distributions of the medians and widths of the 90% credible interval for each of those individual parameter estimation runs. And basically the point is that once you include this variability in the PSD, the variation between runs in both of these measures is smaller. So this kind of reduces the range of statistical fluctuations due to changing the PSD. Okay, and we can also look at their comparison between their hybrid approach and the analytic off-source marginalization. So here they're showing the chirp mass posterior for the same event that's been analyzed with 3 different PSDs, again calculated using data from different times. Here, this is what you get when you assume the PSD is perfectly known and fixed. These are the results with the analytic student T likelihood, and here with their variable PSD. And if, in the ideal case, all these 3 curves would match up perfectly. And so you can see that for the analytic marginalization, there's better improvement compared to using the fixed PSD, but they find the best match between the results when they use their variable PSD method. And this tells us that the variation between runs is not due only to the statistical uncertainty in the estimate of the PSD, but there's also some non-Gaussianity that can kind of be fudged more acceptably in their hybrid model than in the off-source marginalization. And a comparison of the base factors shows kind of a similar conclusion. So these are the base factors computed using the 3 methods, and basically you want them to be robust against your choice of PSD. So they find that their hybrid approach produces the best consistency in the base factors. Okay, we can also look at the results using the on-source marginalization. So here are posteriors on the chirp mass ratio, distance, and chi-effective for the first 10 binary black holes detected by LIGO and Virgo. In blue is the PSD marginalized result, and in orange, the median. And in general, you can see that there's some variation, but the agreement is pretty good between the 2 of them. And so if we quantify that, we find in general that the change in the width of the 90% credible interval is on the order of 10% between the median or marginalized results. And that this variation in the posteriors between the two methods doesn't depend on the SNR of the signal. So how well you can characterize the properties of the noise in that segment is not correlated with the strength of whatever signal may or may not be in there. And we do find larger variation in the posteriors than when marginalizing over the off-source uncertainty. So perhaps this means that the intrinsic uncertainties associated with the on-source method are larger than for the off-source. And here you can see a comparison in the change in the width of the 50% sky area and 90% sky area fractionally, and then also the absolute values. So in some cases, the sky area gets bigger. In some cases, it gets smaller. So it's not always the case that this introduces more uncertainty. Okay, we can also look at how this compares with other systematics. So on the right here is a nice plot from a paper by Ethan showing the results for GW 170608 on the total mass ratio chi-effective and chi-p. In red is what happens when you include the uncertainty in the calibration. So I won't have too much time to talk about calibration, but basically our detectors need to be calibrated. We're not always sure how well they're calibrated, and so you can basically marginalize over the uncertainty in that calibration when you're doing parameter estimation. And there are various ways to do this. Typically, we assume some spline fit, but there are also more physically motivated ways, including the method introduced in this paper. And so in blue are the results when you don't include this calibration uncertainty, and you might be thinking, well, I can't see the blue, and it's because it lies directly behind the red. So at least for this event, calibration marginalization does not really have a big effect. And in the middle, you can see the same results, but using the on-source PSD marginalization. So at least in some cases, there's a somewhat visible difference between the two, but again, they're in general pretty consistent. And on the right, you can see the comparison using the two different waveform models that Geraint discussed in detail. So I would say in general, in my opinion at least, the order of importance of the different systematics considered here increases as you go from left to right across this plot. And again, things like calibration will become a lot more important when you're in the regime of signals that have SNR in the hundreds, but for now, I'd say, yeah, left to right here. Okay, and just to quickly mention some alternative approaches, instead of kind of doing this in two steps where first you fit the PSD and then you fit the binary parameters, you can do it all in once. And so there was a paper by Edwards a few years ago that used a non-parametric Bernstein polynomial prior on the PSD and inferred it simultaneously with the properties of a core collapse supernova event. And so this is an on-source PSD method that they say does not require the assumption of stationary and Gaussian noise. And you can see one of their estimated PSDs here for the particular event that they were analyzing. And then earlier this year, Katerina had a nice paper showing how you can do basically the PSD fitting, the compact binary parameter fitting, and any sort of glitch fitting all at once. Here you actually can get the Bayes factors out for this marginalization over the on-source PSD, which is really nice. And here you can just see some results basically when you do this all three scenarios at once versus assuming there is no glitch in the signal, and we'll hear more about the effects of glitches in the next talk by Ben Farr. Okay, so pretty much we've seen that with the different methods for PSD marginalization, the effect on the binary parameter posteriors is pretty small, on the order of 10%. However, it seems to be that the Bayes factors are more sensitive to this. And so now I'll show a few analyses where this actually is important. So it turns out that incorporating this uncertainty on the PSD is required for analyses that stack these Bayes factors for individual events, or for analyses that include these long duration transients, so longer than what we typically analyze for CBCs. Okay, so one example is this paper by Sharon Banerjee from a couple years ago, where they demonstrated a method to search for the long-duration BNS post-merger signal from a spinning down millisecond magnetar. And so the details of the model are not really important here, but basically, instead of just taking the model in the frequency domain, they use a time-frequency map. And so the likelihood here is not just a function of frequency, it's a function of time and frequency. So how this works is you take your long stretch of data and split it up into short segments, and then you basically just stack the periodograms of the individual segments, or the Fourier transforms of the individual segments. And so in this work, they found that there's a bias in the millisecond magnetar parameters that they recover if they don't include this uncertainty in the PSD. And they corrected for this by using the analytically marginalized off-source likelihood. Okay, another example is the Bayesian coherence ratio. So this is a way to quantify the significance of an event in a more Bayesian way. And so it derives from the idea of the BCI, which is just the Bayes factor between a coherent signal in multiple detectors versus individual glitches in each of the detectors. So this was introduced by Feach and Vecchio, and they make the conservative assumption that glitches can be modeled using the same binary parameters as real compact binary mergers. It's just that the parameters that you recover if you search for a glitch in two detectors simultaneously will be incoherent. And so you can construct this Bayes factor by basically taking your signal evidence, assuming a coherent signal in both detectors, and then dividing that by your individual evidences for glitches in each of the detectors independently. And so you can extend this BCI idea to what's called the BCR, or the Bayes coherence ratio. And this is an odds comparing the coherent signal hypothesis to the incoherent glitch or Gaussian noise hypotheses. And it was first introduced in a paper by Max Isi. So this is what this looks like. It has similar terms here, the signal evidence and then the glitch evidences. This is just the noise evidence, so assuming no signals and no glitches. But it's multiplied by these prior odds. So you need some prior odds for having a signal and also some prior odds for having a glitch in the particular data segment that you're analyzing. And then you just multiply over your individual detectors. And so Avi Vajpayee recently led a search using this method to look for intermediate mass black hole signals in data from LIGO's third observing run. And so here they treat the BCR as a frequentist ranking statistic because those prior odds that they choose don't necessarily correspond to the astrophysical prior odds. So the idea is that you tune these pi hat parameters to give you the best separation between the foreground and background distributions of this BCR. And so here you can see a plot of the survival function, which is just 1 minus the CDF for the background and the foreground that they were working with. And this is just as a function of the log of the BCR. And you can see two signals highlighted here. One is GW170814, and the other is GW170817A, which was found independently by another search pipeline developed out of IAS. And so the top panel here shows this foreground and background separation when you calculate the BCR, assuming that you know the PSD, while the bottom shows the same, but including that off-source analytic marginalization. And so you can see that once you more accurately model the noise, you get a more pronounced separation between the foreground and background distributions, which is what we want. Okay, this idea can also be extended into a full astrophysical odds. And so here, instead of tuning the prior odds on signal and glitches, you actually infer them. This method was developed in a series of papers led by Greg Ashton. And so you can see here the definition of this astrophysical odds between the signal hypothesis and the noise hypothesis in one particular segment. So in this case, your prior odds is this duty cycle parameter psi, which is just the fraction of segments that you analyze that will contain an astrophysical signal. And so in their analysis, they assume that this is just proportional to the rate that we infer using the binary black hole population. What is unique is that they introduce a series of hyperparameters for the noise model. So again, assuming that your glitches are akin to binary black hole mergers, then you can actually model their distributions of masses and spins. And so you get a more accurate description of what your noise or your glitch population contaminating your astrophysical population looks like. And this also includes, in this hyperparameters, this includes the glitch rate. And so you marginalize over all those glitch hyperparameters, and this allows you to estimate this astrophysical odds. So here they're calculating the odds for 3 signals from LIGO's first observing run. And what I really want to emphasize are these 2 columns. So here is the Bayes factor just between the signal and noise hypotheses for each of these signals, computed assuming the PSD is known, while in the second column is what you get when you instead change your likelihood to be that off-source marginalized likelihood. And so particularly for this GW15-1216 event, which was a lower significance event, again found by the IAS pipeline, this changing the likelihood to account for the marginalization drastically reduces the Bayes factor for signal to noise. And so they conclude that the terrestrial probability of this event is 0.97, so very high. Okay, and in the last few minutes, I will talk about another application where this is important that Ariana introduced during her talk. So instead of assuming that that duty cycle is just proportional to the rate, you can actually infer it. And this is done by basically performing Bayesian parameter estimation on every single segment of data. And the idea is that the Bayes factors will be particularly sensitive to subthreshold signals, so you can use this to look for an astrophysical stochastic background due to compact binary mergers. And so this is the statistically optimal method to search for such a background because we know that it's non-Gaussian. We know that binary black holes only merge on average every like 200 seconds in the universe. So assuming that this background is always on and that it's well described by a Gaussian stationary background actually penalizes you. And so here, once you relax that assumption and include also the fact that you know deterministically the model for what those sources should look like, it leads to a drastic improvement in the time to detection of this background. And it was first introduced in this paper by Smith and Thrain a few years ago. And so this is the likelihood for this duty cycle parameter given a set of data segments D. It's just a mixture model where you're multiplying xi by the signal evidence and adding it to 1 minus xi plus the noise evidence. In practice, this noise evidence needs to be expanded to include all the possibilities of glitches and independent detectors, but for simplicity, we can just write it like this. And so what happens is that you need, obviously, very accurate evidence estimates to be sensitive to those weak signals. And as you can see in this nice plot provided by a column, if you don't include the uncertainty in the PSD when you're calculating this posterior on the duty cycle, you actually get a bias. So you'll misestimate the rate of binary black hole mergers in the universe. In blue, you can see the posterior once you do include the off-source marginalization, and it includes the true value here. And so this is one situation where you actually also need to account for those off-diagonal elements in your noise covariance matrix. So merging these 2 likelihoods to account for these different properties of the noise is a next step for this search. Okay, so then I'll just summarize. We saw that there are 2 main methods for calculating and marginalizing over the uncertainty in the PSD. With the off-source calculation, you can analytically marginalize over the uncertainty. with Onsource, you can do a numerical marginalization, or you can just do everything at once, and that will solve many of the problems. And so for the individual posteriors, the variation due to this marginalization is small, on the order of about 10%, but it's the base factors that are really more sensitive. And so this means that we can't neglect this effect when we're analyzing basically an ensemble of data segments to determine some sort of Bayesian-based significance that requires those sensitive base factors, and then when we're looking at long signals in both the time and frequency domains. I think that's all.